Hi, Assalamualaikum warahmatullahi wabarakatuh. I'm going to talk about the introduction to eigenvalues and eigenvectors. Here you are given a square matrix. The size of the matrix here is n by n, square matrix. And here x is a column vector. So the size of this is n by 1. And lambda here is a scalar, and we have here the relationship between matrix A, vector x, and lambda. And this is the starting point of what is known as the eigenvalue problem. Now, the idea here is we would like to find the solution for column vector x, and of course it is possible to get all the solution equals to vector 0. It is a possibility when both sides are 0. So when we have what is known as 0 solution here for all, then it is known as the trivial solutions, and usually this is not what we are interested at. What we are interested here is the occurrence of non-trivial solutions for this vector x. So this is what we are looking to find, and it may exist if we have managed to get the values of lambda. So lambda here is known as the eigenvalues of matrix A. So I'm just going to highlight that. So lambda here is eigenvalues of matrix A. It is possible to get the solutions for column vector if you are able to find the values of lambda. Now, once you are able to find the value of lambda, you'll be able to get the values for x, and x here, which is a column vector, it is known as eigenvector corresponding to that specific value of lambda. So these are perhaps two definitions that you might want to pay attention to. So lambda here is eigenvalues of matrix A, and then based on that, you can have or you can find the values of x. X here will be known as eigenvector corresponding to lambda, to specific value of lambda. Okay. Now here I'm going to explain the process of finding the values of x, which is our column vector. So again, it begins with this point here. We have this equation, and based on that we can rearrange so that we have 0 on this right hand side. So you can see clearly you can rearrange this part so it becomes like this, and then we can consider having just x on one side. So you are factoring a and lambda, and here is what we're having here. We have a minus lambda I. Here is the identity matrix, and the size of it will match the size of A. Remember, what is A? A is n by n matrix. Therefore, if you're talking about this identity matrix, the size of it will also be n times n. So it will match the size of matrix A, okay? So, in order to find the non-zero solution, this is what we're looking for, the non-zero solution for vector x. We can do that, or we can obtain this type of solution if the matrix of coefficients is singular. What it means mathematically is that you have to be able to get this. You have to be able to find the values of lambda based on this equation. You have to try and solve this equation here. So what it is, so it is finding or setting. So you're going to set the determinant of this matrix equals to 0. Okay, so you're going to set determinant of this must be equals to 0. So you're talking about this equals to 0. And this whole thing here is called the characteristic equation of matrix A. So this is the name of it. This one here is called the characteristic equation of matrix A. And when you solve that, you'll be able to get the eigenvalues of lambda. And once you have the eigenvalues of lambda, you can substitute this result into this part here. So you can go back to this here, this equation here, you can substitute the values of that into it, and you'll be able to obtain the eigenvectors x. Okay, maybe I shall write again all the step. So the step here is, okay, hang on, let me just erase a few things here. Okay, so again, let me just explain the process. The first step is, this is step 1. Okay, we come up with this expression, and then you find the values of lambda based on this equation here that you've considered. Once you have got the values of lambda, you will go back to this part here, which is similar to this one. Okay, so these two equations here are the same equations that you have to consider. So this is step 3, and then you'll be able to get the eigenvectors, which is x. Okay, perhaps with examples you are able to see the process clearly, and that's what we're going to do. Here is the simple matrix of 2 by 2. A is our matrix given as such, and you are asked to find the characteristic equation. So remember, what is characteristic equation? Characteristic equation is this part here. So this is characteristic equation. And then you need to find eigenvalues and eigenvectors of the matrix. Okay, so according to what I have outlined here, the first step is, of course, to consider this equation. So I'm just going to write down here, so consider determinant of A minus lambda. This is the identity matrix. The size has to be the same as matrix A, so this is 2 by 2, so we know that this is the rendition of identity matrix with size 2 by 2, right? And this must be equal to 0. So this is the starting point that you have to consider. This is what we need to consider. And I'm just going to do the process bit by bit. Okay, so I'm just going to start with finding what is A minus lambda multiplied with the identity matrix. So here is A minus lambda I2 is just matrix A minus lambda. Lambda is unknown, remember, we need to find what's the value of lambda, and identity is 1 0 0 1. So this is the identity matrix. Simplify that and you will be able to get at this position here, it will be so for this position, okay, for this position it will be 2 minus lambda, 2 minus lambda times 1, and at this position here it will be 2 and 0, so 2, and then here will be 5 minus 0, lambda times 0 is 0, so 5, and for this one is negative 1 negative lambda. So that is A minus lambda multiplied with the identity matrix. Next is I'm going to consider what is the determinant of this one here. So determinant of A minus lambda I2, this is equal to, well, you know how to find the determinant of this matrix. Well, you need to cross multiply these two items minus this cross multiplying the two items here. So that would be 2 minus lambda, negative 1 minus lambda, minus 2 times 5 is 10. Simplify that. So that becomes 2, negative 2 lambda, positive lambda squared minus 10, and that can be further simplified as this is lambda squared, lambda negative 2 lambda, so negative lambda, negative 12. And next we are going to consider the whole thing. So here is, we're going to consider the whole thing. So therefore, the characteristic equation of matrix A is, so consider the whole thing now, so that will be lambda squared minus lambda minus 12 is equal to 0. So this is the characteristic equation. We have done that, and based on the characteristic equation you can find the eigenvalues by solving this quadratic equation. Okay, right. Next is okay, I'm just going to write down here the characteristic equation is lambda squared minus lambda minus 12 is equal to 0. So based on this, so this is the characteristic equation, you can easily get the values of possible lambda when this equation is 0. So that will be, if you consider lambda, here is 4 times 3 must be 12, and it has to be a negative sign, and here is negative lambda, so we know that this has to be negative, this has to be positive. Therefore we can consider lambda plus 3, lambda negative 4 is equal to 0 based on the above. Okay, based on the above, we know that lambda plus 3 is equal to 0, or lambda minus 4 is equal to 0. Therefore lambda can be negative 3, or lambda can be equal to 4. And for simplicity, we can just say this could be the value of lambda 1, this could be the value of lambda 2. Now, since you have managed to get the values of lambda, which is the eigenvalues, you will go on and proceed to obtain the values of vector x. So in order to do that, we need to consider plugging these values here of lambda into this equation, a minus lambda I2 vector x must be equal to vector 0. So this is the equation that you need to consider next in order to find the values of x, vector x. Okay, and since we have two values of lambda, we're going to consider them one by one. Therefore, we shall start with, for lambda 1 equals to negative 3, just going to label this equation as equation 1 so that it makes my life easier. So equation 1 then becomes, what is A? A is 2 to 5 negative 1, 2 to 5 negative 1 minus, I'm just going to plug in the value of lambda. So lambda 1 is negative 3, so negative 3 lambda, identity matrix 1 0 0 1. Just follow this given equation here. Okay, and here is, well, value of x here must be x1 and x2. How do I know it must be x1 and x2? Because this is a 2 by 2 matrix. The result here is going to be 2 by 2. So it has to be multiplied with a column vector. A column vector means you have one column only. And the rows here has to be two rows because it has to match this part here. So this part here, when you simplify that, you know that you will get 2 by 2. Therefore, this must be 2 by 1. One column, because you're talking about, again, the column vector. 2 rows must match this number of columns in this part. Okay, right. So this one must be equal to 0 and 0. So the result of multiplying 2 by 2 with 2 by 1 will give you a 2 by 1 matrix for 0 and 0. And we can just simplify this. What's going on here? We can simplify that with well, here is 2 to 5 negative 1, negative positive, so multiply that inside, 3 0 0 3, x1 x2 0 and 0. Okay, and this can be considered as 2 plus 3 5, so I'm just going to write it down here, 5, and then 2 0, so 2 and 5, 2 and 5, and then negative 1 3 is 2. So this is the matrix right next to x1, x2. Here is 0 and 0. Now remember that we would like to find the values of x1 and x2. So these are the unknowns, and how do we solve it? We have known that in order to solve this, you can consider the augmented matrix, okay, in this notation. And clearly you can see that this row here is exactly the same as the first row. So you should get the idea that if you do some sort of elementary row operation, you can get rid of this whole thing here and it all becomes 0. Therefore, I will consider this operation R3 plus negative 1 R, sorry, not R3, R2, negative 1 R1. So here 5, 2, 0. 5 minus 5, 0. 2 minus 2, 0. 0 minus 0, 0. Next, what I can do is I can turn this value into 1. So I will multiply that with 1 over 5, the first row, 1, 2 over 5, 0, 0, 0, 0. And I have simplified the look of our augmented matrix. Based on that, I can then, well, this part here, we can't get any equation out of it. And for this one here, you can see that this is x1 plus 2 over 5, x2 is equal to 0. So we only have one equation, but two unknowns. Therefore, one of the unknowns here is going to be the free variable. And based on that, we know that x1 is negative 2 over 5 x2. And we're going to let x2 equals to t, where t can be any real number. Therefore, x1 is just negative 2 over 5t. Now we can represent the answer of x1, x2 in this notation. We have x1 negative 2 over 5t, and this one is t. And you can consider taking factor sum of this thing out. So if we factor out 1 over 5t, the result here is going to be negative 2 and 5. Okay, therefore, what we can write down is we can write down the eigenvector corresponding to lambda equals to negative 3, lambda 1 equals to negative 3 is negative 2 and 5. So this is we're not done yet, actually. This is the first part for it. So hang on. So this value here is taken right from this one. Okay, this is the eigenvector corresponding to lambda 1 is equal to negative 3, and we are not done yet because we still have lambda 2 equals to 4 that we need to consider doing this whole process again. Okay, all right, shall we do that? Since I'm running out of space, I'm just going to, well, erase everything on this slide, and I'm going to consider lambda 2, which is equal to 4. So for lambda 2 equals to 4, oops, okay, I'm just going to erase this part as well. So for lambda 2 equals to 4, what we have is, again, we need to consider this equation. Okay, so this here will become, so it will become matrix A is 2, 2, 5, negative 1 minus, what is lambda? Lambda here is lambda 2, which is 4. Identity matrix. This is x1, x2, 0 and 0. And then we can simplify this inside this bracket here. the result is going to be, well, 2 minus 4, negative 2, 2 minus 0 is 2, 5 minus 0 is 5, negative 1, negative 4, negative 5. This is x1, x2, 0 and 0. Again, our objective is to find the values of this unknown, and you can do that by considering the augmented matrix. And I'm going to start off this process by considering this, turning this value into 1. So I need to multiply that with negative 1 over 2 times the first row. So I shall have 1, and here is negative 1 and 0, 5, negative 5 and 0. Now I need to consider turning this value into 0. That can be achieved if I consider R2 plus negative 5 R1. 5 minus 5, 0. So again, wait, let me just write down the first row. So 5 minus 5 is 0, negative 5 plus 5, 0, 0, 0, 0. Again, what we have here is we have the simplified version of augmented matrix. However, this part here is, well, nothing can be gained out of it, so we only have this to consider. And here it means we have x1 minus x2 is equal to 0, therefore x1 must be equal to x2. Again, notice that we only have one equation, but we have two unknowns to solve. Therefore, one of the variable is going to be a free variable, and we're going to just let x2 takes any value of t. T is could be any real number, and because of that, x1 is just equal to x2, which is just equal to t. Well, since we have that, we can then write our answers in terms of this notation, which is t and t, and this can be further factorized as such. You can take out t, 1 and 1. Therefore, the eigenvectors corresponding, okay, to lambda 2 equals to 4 is 1, 1. Okay, so this is the end of the whole question asked here. We have managed to get the eigenvalues and the eigenvectors of this particular matrix. Okay, shall we go on with the next example here? Alright, so I'm just going to speed up the process, assuming that you guys have understood what is need to be done. Okay, so we have here this matrix, and I'm going to start considering this equation, determinant of A minus lambda I. This is a 2 by 2 matrix, so this is 2 must be equal to 0. So this is the starting point, and I'm going to call this equation 1. Okay, and like I've shown you earlier, I'm just going to do the process bit by bit. So I'm going to start with finding what is A minus lambda I2. This is equal to negative 1, 2, 0, negative 1, minus lambda is unknown. That is what you're looking to find, and this is the identity matrix. And based on that, you will have negative 1, negative lambda, 2, 0, 0, negative 1, negative lambda. Okay. Next, what I can do is I can then consider finding the determinant. So determinant of A minus lambda I2 here, which is given by this one, is going to be, well, you know how to find the determinant of 2 by 2 matrix. Multiply this, negative 1, negative lambda, negative 1, negative lambda, plus, minus, the result of this is 0. And if you consider this, you will have negative 1, positive 1, positive lambda, positive lambda, positive lambda squared. So this is the result when you expand this part right here. Therefore, okay, So based on this, the characteristic equation of A, which is what we're looking to find here, is given by this equation. So it's going to be equal to, well, you simplify this part, it becomes lambda squared plus 2 lambda. Okay, lambda squared plus 2 lambda plus 1 is equal to 0. So this is the characteristic equation. Now, based on this characteristic equation, you can proceed and find the values of eigenvalues. Okay, you can find the eigenvalues. So when you have this is equal to having so based on this, I'm just going to write it properly. So based on lambda squared plus 2 lambda plus 1 is equal to 0, this can then be written as, it can be written as, here we have lambda plus 1 is equal to 0. And clearly, because of that, we only have the same value of lambda. So that means lambda plus 1 squared is equal to 0. Therefore, lambda is just equal to -1. We only have one value of lambda, okay? Next, this is the eigenvalues. Once you have got the eigenvalues, you can consider moving forward and determine the eigenvectors of the matrix. So for lambda equals to -1, equation of A minus lambda I2 vector x then becomes, I'm just going to substitute matrix A and so on. So matrix A is, okay, -1, 2, 0, -1, -1, 2, 0, -1. This is matrix A minus lambda. So lambda is -1. This is the identity matrix. And this is x1, x2, and this is vector 0. So simplify what is in the round bracket. So here we have -1, 2, 0, -1, negative, negative, positive, 1, 0, 0, 1, x1, x2, vector 0. And here we can simplify the matrix here. We have -1 plus 1, 0. This is 2. This is 0. This is 0. x1, x2, 0, and 0. Based on this, we know that our objective or our aim is to find the unknown values here. And we can do that if you consider the augmented matrix, which is going to look like this. And I think this is already in the simplified form. You don't need to do anything much, I think. So you can just create an equation out of it. Of course, for this one here, nothing useful can be gained from it. But for this part here, you can see that this gives you 2x2 is equal to 0. So you can see there is only one equation but two unknowns. Therefore, one of the unknown here will be the free variable. Now, based on this equation here, we get that the values of x2 is going to be 0. So what is the value of x1? Therefore, x1 here must be the free variable, and we're going to let that becomes represented by t, where t is any real number. Okay, so since we have obtained the result here, oops, sorry, I don't have space anymore. I'm just going to write it here. So because of that, write down your result. x1, x2 is just t and 0, which then can be written in this way. Okay, now I'm not going to write down the whole thing, but you know that here is the eigenvectors corresponding to lambda -1. Okay, so you can write it down properly in this full sentence. Therefore, the eigenvectors corresponding to lambda -1 is given by this part here, 1 and 0. Okay, right. Here is the last example related to eigenvalues and eigenvectors. Okay, so the matrix A is given by such. This is a 2 by 2 matrix. Again, the process is simple. We're going to start off with this equation, determinant of A minus lambda I2 must equal to 0. This is the starting point. And then I'm just going to start off with finding what is A minus lambda I2. So A is 2, -1, 1 and 2, minus lambda is unknown, 1, 0, 0, 1. And because of that, you can simplify this with, so 2 minus lambda at this position, -1, 1 minus 0, 2 minus lambda. So here is the part here. I'm just going to focus on this part. Next is I need to find the determinant of this, determinant of A minus lambda I2. Well, we can just cross multiply minus the result here of multiplying the cross items. So here we have 2 minus lambda, here is also 2 minus lambda, you square it, plus, since this is negative will be plus 1. Okay, and that can be simplified as 4 minus 4 lambda plus lambda squared plus 1, and this is lambda squared minus 4 lambda plus 5. Okay, based on this, we can then answer what's the characteristic equation. The characteristic equation of matrix A is this whole thing equals to 0. So this is the characteristic equation, and the answer is lambda squared minus 4 lambda plus 5 is equal to 0. Now, since you have obtained the characteristic equation, you can go on and try to find the eigenvalues. Well, the eigenvalues here is going to have complex number, okay, because we can see that remember when you have this equation ax squared plus bx plus c, and if you consider b squared minus 4ac and you get a negative value, that means you'll be dealing with imaginary number. So here A is 1, this is B -4, C is 5. So if you substitute that value, B is -4 squared minus 4, A is 1, C is 5. The result is 16 minus 20, -4. And you know that this can be solved where if you consider this equation, if you want to know what lambda is, it cannot be solved like, for example, like this one. Simply by looking at it, you will be able to get simple factorization. You can factor and get lambda plus 1 and lambda plus 1 because the equation given here is simple. But what we have over here is there's no other way, but in order to solve for the value of lambda, you need to consider this equation. So lambda is -b plus minus. So here is the formula, which I'm sure a lot of you guys are already familiar with that. So this is the formula, okay, in order to find lambda. So of course -b is -4 plus minus the square root of b squared minus 4ac is 4ac is already calculated here, so I'm just going to write down -4 over 2 times a, 2 times 1, and this becomes 4 plus minus we know that negative 4 is just 4i squared. Remember, negative 1 is equal to I squared. Okay, just in case you guys have forgotten the idea, I squared is equal to negative 1. So this is something that you should remember. So what we have here is actually negative 4, which can be written as negative 1 times 4, and so you can replace negative 1 with I squared. Okay, right, then shall I just continue? This is divided by 2, and by doing that you can find the square root of 4i squared, so it becomes 4 plus minus 2i over 2, and that can be further simplified as, let me just erase this space. So that one here can be simplified as 4 over 2 is 2 plus minus I. So 4 over 2, 2 over 2i, so plus minus I, okay? Therefore, we can say that we have two values of lambda. We can say lambda 1 is 2 plus I, and lambda 2 is 2 minus I, and these are actually eigenvalues. So we have managed to answer this question of finding the eigenvalues. Now, based on the eigenvalues given, we should go ahead and try to obtain the eigenvectors. And we're going to do it one by one. Perhaps we should consider lambda 1 first. Therefore, for lambda 1 equals to 2 plus I, the equation here, a minus lambda I2 x vector 0, then becomes, well, vector A is 2, negative 1, 1, 2, minus lambda here is 2 plus I. This is identity matrix. This is x1, x2, this is vector 0. And if you simplify the whole thing here, it becomes, well, 2 minus 2 minus I. So 2 minus 2 minus I. At this position here, it becomes negative 1. Here it becomes 1. This one is 2 minus 2 minus I. Okay. Right, this is x1 and x2. This is equal to 0 and 0. Of course, you can see that this can be simplified. 2 minus 2 is 0. You can just get rid of it. Similarly, this is what you can get rid of it. So we have a simplified matrix. And again, this is the unknown, and you want to find what the values are. So what you can do is you can consider the augmented matrix that is going to look like this: negative I, negative 1, 1, negative I, 0 and 0. Now what I can do is I can consider turning this value, changing the row so that 1 here is at the top. So I can do that. Let us do that then. We're going to interchange the row, R2 interchange with R1, and here we have 1, negative I, 0, negative I, negative 1, 0. Based on this, I need to get rid of negative I. So in order to get rid of negative I, what I can do is I can consider the change in row 2 plus I times with the first row. So 1, negative I, 0. Negative I plus I times 1 is going to be 0. Negative 1, negative I squared. Remember, I squared is negative 1. So negative 1, negative I squared. So it's going to be positive 1. Negative 1, positive 1 is 0 and 0. Yep. Okay, now this is already a simplified version, and of course we can see that for this part here nothing useful can be gained out of it. But for this one here, what we have is x1 minus I x2 is equal to 0. Therefore x1 must be I x2. Here we have only one equation and two unknowns. Therefore one of it will become the free variable, and we're just going to let x2 be the free variable. Okay, let x2 equals to t. Therefore x1 is just I x2, which is it. Okay, so t here is any real number. x1 x2 is just going to be written as it and t. This can be factored out as such, I and 1. Therefore the eigenvectors corresponding to lambda equals to 2 plus I, okay, lambda 1 equals to 2 plus I is I and 1. Okay, not done yet, because we still have to find the eigenvectors associated with this one here, and I believe you can try and do it on your own. So I'm just going to leave the answer for this one here. The eigenvector corresponds to lambda 2 equals 2 minus I is this guy, negative I and 1. Okay, so this one you can try and do it on your own. Good luck with that. Thank you very much for watching, and I'll see you in the next video.